Hello, myself Dr. SaikatDutta. So we have a syllabus that includes aromaticity and reactivity of aromatic compounds. So what I have done, make a short video about basic concepts, more like a recap of aromatic compounds and aromaticity, and the basic reactivity behavior, which you can go through the video and try to understand the basic line concept, and most of it is hopefully a recap, and you can come prepared in the class, and we can go for more examples and detailed mechanism, application oriented questions, and finally stepwise synthesis of real life multi-substituted aromatic compounds, how to synthesize them, what are the logical steps. So this short video will tell you the what aromatic compounds are, what are the criteria for one compound to behave as aromatic compound, what are the reactivity patterns compared to other compounds, and what are the reactivity that the aromatic compounds can undergo. So the next slides, what I have done is more like a recap that what are the criteria for a molecule to behave as aromatic compound. So if you remember, the Huckel's rule is a very simple rule. It says that if a molecule is cyclic, that means it has to be a ring structure, like the first example. I mean, all of them are ring structure. It has to be planar. Planar means that all the atoms, it has to be on the same plane. And conjugated. Conjugated means that all these carbons, let's say, or here a heteroatom nitrogen, all these atoms, they have to have at least one pi electron, and the total number of pi electrons within this ring, it has to be 4n plus 2, where n is an integer. N can be 0, 1, 2, 3, etc. So for example, if n is 0, then you will have 4 into 0 0 plus 2, so 2 pi electrons. So 2 pi electrons, if you have that, then it will be an aromatic compound. If n equals to 1, then 4 into 1, 4 plus 2 equals to 6. So total 6 pi electrons in the cyclic structure, then it will behave as aromatic compound. So what are the anti-aromatic compounds? Some of the parameters are exactly same. So some molecules which are cyclic, planar, conjugated, but they have 4n pi electrons. That means that they can have 4 electrons or 8 electrons, 12 electrons, etc. So they will be considered anti-aromatic. So anti-aromatic means the quality or the properties that aromatic compounds show, they show the opposite. And any other compound that doesn't follow all these parameters, let's say non-planar or non-conjugated, they will be considered as non-aromatic. So now look at these 6 examples. The first example, if you go through the parameters, it is a cyclic molecule, is planar, is conjugated, that means each of these atoms, 5 carbon and 1 nitrogen, they have at least 1 pi electron. And since it has 4 into 1 plus 2, total 6 pi electrons, you can count starting from this one, 1, 2, 3, 4, 5 and 6. So this molecule will be considered as an aromatic compound. Look at the second example. This is called pyrrole. Now this has a 5-member ring. That means this is a cyclic structure, and all the atoms, so 4 carbons and 1 nitrogen, they are all on the same plane. It's conjugated. You can see the double bonds over here, and don't forget the lone pair on the nitrogen atom. So that lone pair is actually conjugated through the ring. So how many electrons can you figure out in this ring? It will be 1, 2, 3, 4, and then the lone pair, that means 2 electron, so it will be total 6 electron, which actually satisfies the Huckel's rule. So this compound pyrrole is an example of aromatic compound. Third example, look at that. It's a cyclic molecule, 4-member ring. It's a planar molecule, all the carbon atoms on the same plane. And how many pi electrons are there? So 2 double bonds, that means 4 electrons, 4 pi electrons. So this actually following this example over here. So this compound is actually anti-aromatic. Look at the number 4. This is a cyclic molecule. It has 2 double bonds, that means 4 pi electrons. However, the carbon number 1, 2 and 5, 6, they are planar, so on the same plane, because both they are conjugated. They have pi electrons. However, the number 3 and 4 carbon, they are sp3 hybridized. That means they are not on the same plane as these 4 carbons. So they are on a different plane. That means the molecule itself is not planar. So both for aromatic and anti-aromatic compound, the molecule has to be planar. That means this molecule, cyclohexadiene, this is a non-aromatic molecule. Look at number 5. This is a 7-membered ring. Count the number of carbon atoms. You can find out this is a 7-membered ring. This is a conjugated molecule. And how many pi electrons are here? So plus charge means this carbon has no pi electron. It's just an empty orbital. 1 electron over here, 2, 3, 4, 5 and 6. So 6 means 4 into 1 plus 2. So this molecule is aromatic. Whereas number 6, this compound over here, is very similar to number 5. The only difference is this carbon over here doesn't have a positive charge. That means this carbon is connected to 2 hydrogen atom. So that molecule, this carbon atom is sp3 hybridized, and all the rest of the carbon atoms, all 6 carbon atoms, they are sp2. So this carbon over here is actually out of plane. That means the whole molecule will become non-planar. If it is non-planar, then they don't fall into the category of aromatic or anti-aromatic compounds. So actually number 6 is non-aromatic compound. Now the question is that how different are the reactivity of aromatic compounds compared to the non-aromatic compounds or simple olefins, let's say. So we take 2 examples. One example is the cyclohexene, which is a standard olefin, and benzene, which is considered as a aromatic compound. So now we will see a few reactivity behavior that will show us that a simple isolated olefin is different than an aromatic compound, which is basically a conjugated olefins in a cyclic structure. So when cyclohexene you react with bromine, it instantaneously react, and the bromine atoms, they add across the double bond and form the dibromide. You oxidize it with a strong oxidant, potassium permanganate, and you make the diacid. You add hydrogen across the double bond, it saturates the double bond and form a cyclohexane. You try the exact same reaction on benzene and none of them actually works. So if you add bromine to a benzene liquid, then there is no reaction at room temperature. You add potassium permanganate, nothing happens. You try to hydrogenate benzene, 1 atmosphere hydrogen in presence of a catalyst, there is also no reaction. That means the reactivity of these aromatics is way different than the simple olefins. So something is stabilizing the aromatic compounds, so that's why their reactivity is different. Now the question is that what are the ways that these molecules will react? So the first thing you have to understand that these molecules is stabilized because of the aromaticity. So the way it can react, the aromaticity has to be maintained in the product. So whatever happens in the intermediate, momentarily it might lose the aromaticity, but it has to regain the aromaticity in the final product. So one way is that you have to replace one of these CH bonds, which is sp2 carbon and hydrogen mentioned over here, and then you make a carbocation intermediate. So simply one of the double bond, the arrow goes to the electrophile, positive charge is developed on the carbon, and the electrophile is attached to this carbon over here. So this carbon right now is a sp3 hybridized carbon. You lose the aromaticity for a moment, and then you lose the proton and you regain the aromaticity. And look at the difference. The hydrogen was there and the hydrogen is being replaced by E. So that's one way of making the derivative of an aromatic compound, for example benzene.